everyone. My name is Sam Nasser, and this is the Cleveland C# DD.net user group. The meetings are free of charge and open to the public. We meet here every fourth Thursday, and the topics vary anything and everything related to .net. Tonight we have Pat Toner, who's going to be presenting on Ethereum. Just a couple overhead items before we get started. Meeting information can be found on meetup.com. Also, the Wi-Fi password is ROC3001. And that's for the ROC3, either 5 gigahertz or 2.5 gigahertz network. Either one would work with the ROC3000 password. There's pizza and pop over in the corner, courtesy of Inito. We have our meeting space that's been courtesy of Tech Systems for the last year plus. And I'd also like to thank Unitas Technologies for providing hosting services where the recordings will be posted later tonight, as well as for the meetup information. The meeting will last approximately an hour and a half to 2 hours. Feel free to jump in with questions at any point in time. We'd like to make it as much of a roundtable discussion as much as possible, despite the auditorium-style seating. Lastly, if needed, restrooms are straight down the hall on the right-hand side for both ladies and gentlemen. Also, if you would please put your cell phones on mute before we get started. So Pat is courteous to come and present to us tonight about Ethereum. He's a blockchain enthusiast. He's been a developer for the Software Guild and an enterprise architect developer for many years. So without further ado, I will turn it over to Pat.
Thank you, Sam. Thank you for coming, everybody. So, like Sam said, I want this to be, for one, I'm here to talk about Ethereum and smart contract development and cryptocurrency kind of things. But, I'm still learning this. I'm not an expert at this, and I definitely don't have all the answers to all the things that you might have questions about. So, I want to make sure you guys know, I'm here to learn too. Talk to me. I'm here to talk. Let's talk about this. I think this stuff is very exciting for reasons I will get to. And I just want to share it and talk to you about it. And hopefully you would also like it. So I have been a enterprise software developer for a very long time. I did stuff in Java for a long time, but I've also written code in C#, and I know the kinds of applications that you tend to write in a professional business software environment. And for various reasons, I think this technology is going to end up being a very natural, good fit for the skill set that you might already have if you are interested enough in C# to be at a meetup like this. So, how many have heard of cryptocurrency? Okay, good. How about Bitcoin? How about Ethereum? Okay, that's still a lot of hands. That's good to know. Hey. All right, so I just want to tell you my understanding of what Bitcoin is and what cryptocurrency is, and to help you get, to understand why I think Ethereum is so neat. So Bitcoin, it was 10 years ago, not today, but very recently. A guy named Satoshi, no one really knows who he is. Could be a bunch of people have theories, I don't know. He wrote a white paper where he described a new kind of peer-to-peer cash system. And he laid out this idea that he had, and that had already written all the code for. So I want to say in Satoshi's story, people kind of put that aside. The first step he did was he sat in hiding for God knows how long and wrote all of the code for Bitcoin. And then, once he was done, set out and wrote this little white paper that described how the system worked. And then, over time, people got interested in that, and they started playing with it. And he had friends that he got to be a part of his project. And they started sending Bitcoins to each other. And over time, other people started getting curious about this idea. They started creating wallets. They started interacting in the system. And then one day, some guy sent 20,000 Bitcoin to pay for a pizza. And on that day, Bitcoin was actual money that was being exchanged for value, for a pizza. Very valuable. The general idea with Bitcoin is that, okay, like you have a database, right? So think of a bank. And a bank, its primary purpose is to keep track of a ledger, right? The bank keeps track of how much money I have, how much money you have, how much money you have, and whenever we want to send it to each other, we go to the bank and we have the bank process this transaction. And what we end up with is we have a trusted authority, the bank people. We trust the people at the bank to keep our balances in check and make sure that they are always accurate and no one can mess with them. And then, like, you know, the banks with do what banks do. Like, you know, they are a huge part of a society and they enable a lot of commerce and et cetera. Bitcoin was like, what if we could have the same idea, we could have a ledger, we could have a database that kept track of everybody's balances, just like a bank, but instead of putting somebody in charge of it, a government or a company or an anybody, Satoshi came up with this math formula, essentially, where everybody had a copy of the database. Instead of there being one copy of the database and the bank has it, everybody has a copy of this database. And to make changes in the database, it relies on something called public-private key cryptography. Essentially, you have an address in Bitcoin in the ledger, and it has a public key, it has a public address, and then you have a password, essentially, a private key. You have a password that gives you sole control over moving money out of that ledger account. So the entire network now has to agree that I sent money to you. So to remove the trusted person in the middle, like essentially we are brute forcing math at this thing with basically uncrackable math functions that guarantee that nobody else has that private key. Let me say that again. That nobody else could move that money from that ledger unless they have that private key. The math is, I don't know, it's like SHA 256 or something. I don't know. Some really high level encryption thing, public-private key encryption scheme that secures the network. And then, like, there's like this battle going on all the time where, like, in order to put information into the database, these people running computers, they're called miners. They're called mining. They have mining computers. And essentially what they are doing is they are racing. They are racing to find the answer to a function. And the winner of the race gets awarded Bitcoin. So that's their reward for securing the network. You have this database that is distributed to all kinds of different people on all kinds of different servers and, you know, devices in your pocket, in a server somewhere, whatever. And everybody is racing to find the answer to a formula because the winner of that, one, they help secure the network. All these people doing this, all this racing is like the part of the brilliance of Satoshi's formula that he came up with. By racing to get this answer, everybody is doing the work to secure the network so that we have mathematical proof that none of the values have changed unless somebody had the private key to do so. Long story short, we use math to get what they call consensus over what a database should look like. And by doing that, like, we can store everybody's account balances there, and we don't need a bank to do it. And I can send money to everybody in this room, and it's virtually free, and nobody can stop us. It's, huh? Yeah, that comes later. So Ethereum then, so the Bitcoin thing, that's been a thing for about a decade now, right? Like, that's been going on, and that experiment is going pretty well. Like, the ideas that they laid down in the white paper, they have held up for the most part. Like, the system's still running. They still have the Bitcoin. It's still a thing. It's worth a bunch of money right now. Ethereum was like, what if, like, there were a group of people that were involved on some level with Bitcoin. These Ethereum people. They were like, what if instead of just ledger balances, what if we could keep other things in that database? What if we could come up with arbitrary data and store it there? Like, maybe it doesn't have to just be our account balances. Maybe we can keep things like maybe like the information for my house deed, or my insurance for my house, or maybe my insurance for my car. Like, maybe we can have other information that's tied in a financial way, usually, to like other financial things, of paying your bills, whatever. Like, what if we could store other information in that database? So, like, there was a big fight, and the Bitcoin people wanted nothing of it, because they're very conservative, really, and they don't like change. And because they bought into a system, and now somebody was trying to change it and do other things, and they're like, nope, we want to see how this plays out. Which I get. So, the Ethereum Foundation, they went and they built an entirely separate thing. And their thing, it works by similar principles. That whole, like, racing for the formula thing, that's called proof of work. That's the name of the consensus algorithm that powers Bitcoin. It also powers Ethereum right now. It's the same kind of thing. But in Ethereum, they've expanded on the idea a little bit. And, like, you know how if you are a Java developer, a C# developer, that's probably more topical. You have a virtual machine that translates your code into some other code that the machine can actually do something with, right? You write C# code, and it gets compiled to, was it CLR? One of those things. And then the machine runs it as machine code. The Ethereum virtual machine has a similar kind of process in it. And the process is called, it runs little snippets of code that they call smart contracts. Now, a smart contract is, here, we're gonna start by building a simple one here in a second. But a smart contract is just code that you write that is, like, the idea is, it is forever, right? Like, I write this, I'm going to write a function that, I don't know, like, very simple use case. We want to gamble on something, right? I'm going to write this function that takes in money from your account, takes in money from my account, takes in something we want to gamble on. And then I'm going to put that out there. And then we can call that function, like I can execute that code we wrote to gamble, and then we essentially get guaranteed execution of this thing because we deployed it to this network that is driven by consensus. I didn't like the way I said that. So what are we trying to do? We have code. Think of it like an endpoint in a C# application, right? You have an endpoint in your application that allows you to log in, right? Ethereum's idea is, what if we took that code and instead of deploying it to a server on Azure that's run by Microsoft, that's using .NET or whatever, what if we put it in this network where anybody could call it forever and nobody could ever change it? And Microsoft couldn't take it down, and you couldn't take it down, and the government couldn't take it down. Nobody could take it down because it is mathematically locked into this network where it's going to be executed forever. Which means you can start building things, hang with me here, you can start building things where like we would normally need a trusted entity in the middle to execute this stuff. Like think of an escrow agreement, right? Like I'm gonna buy this car. I want to buy a car. You're selling a car on the internet. I want to buy this car. And I don't want you to sell this car to anybody else, but it's an hour away and I want to go drive there and I want to check out the car in person, but I don't want you to sell it to anybody else. I'm ready to go. But I also don't want you to just take my money because like if the car sucks, I want to be able to go and stop this transaction from happening, right? So you could build a smart contract. And the smart contract would be a thing that will allow you to take money from somebody's account, hold it in this place that where a bank would typically be. You hold this money there so that I can't touch it, you can't touch it. We're trying to make a transaction between us, and we need somebody to hold the money. Normally, we'd give it to a bank, right? There are escrow companies. This is a big business. You give it to an escrow company. They hold the money for a little bit. They verify. It gives you time. You drive to the car lot. You make sure the car is good. There's no dings. It's the right color. Everything's good. We're ready to go. I approve. I take the car off the lot. You get the money. We didn't need a bank. We didn't need an escrow company. We didn't need anybody to do this. And like, if the title for the car was also part of one of these smart contracts, we could probably put the title directly from my name, or from your name as the car lot, to my name, pay all the fees, and this is just all an automated process that we don't need anybody to run. So like, I think these smart contracts open up doors that, I don't know, like we just have not considered, because the idea that we would have code that could run forever, that nobody needed to maintain, and we could guarantee work the same day it did on the day we shipped it. Like, I put out this smart contract that enables this transaction between me and you to sell this car. It's out there tomorrow. It's out there 100 years from now. It works the exact same way, and I can guarantee it through math. Like, that kind of stuff. This idea is brand new. Like, there is nothing like this. Yeah.
So in the scenario that you were using, right?
Yeah.
Let's say 100 years from now.
Yeah.
There are a bunch of cars that are defunct and depreciated and gone, and the titles that don't exist. So why would we want to have no knowledge about this? Why would we want to store something that really doesn't have any utility?
Well, so in that case, what I was using that for was an example of the transaction between the car dealer and the person buying the car. right? So that would be the transaction I would be trying to automate. So in that scenario, like the title, I don't know. Maybe the title doesn't make sense. I don't know. But the financial part of having an escrow service to facilitate this thing, I think would always be a thing. And like over time, you may move it to a contract that may have more functionality. Like as the dealership, you go, oh, I want the better contract that has this feature and allows me to send it off to whoever, whatever. Like you may choose to use different ones, but the idea would be always the one we're using is one that we could audit. Like somebody who is not buying a car or selling a car could audit this thing and make sure that it actually works the way you say. Like we don't have to just trust that your car arrangement is going to go according to plan, right? Like I can audit this thing and we can make sure that it reads exactly the way you're saying. And then I also don't need to trust you to actually execute the agreement. So like it's more like we remove it allowed us to more directly do business with each other without needing these third parties to facilitate the transaction. I don't necessarily mean that this database of stuff from 100 years ago is going to be super valuable in the sense like I need that record forever. I just mean like there's no like I put the transaction in, right? I send you the money for the car and like you made a deal with the escrow guy where he's going to hang on to the money anyway and you're going to screw me out of my money, right? And like that may not be a problem in America, but there are like 2 billion people in the world who live in a community where they cannot go to their local government and trust that they're going to enforce an agreement between them and buying a car. Like they don't have access to banks, they don't have access to courts, they don't have access to any of these things. And if we can automate those kinds of agreements, we don't need them to have the people. Like we could write a smart contract that automates this agreement of selling a car from me to you, right? And we put the title in some blockchainy database, and like that is like a fun project for me and you, right? But we ship this to some place where this is the only financial system they actually have access to. Maybe for the first time ever, they have access to a bank account and a way to keep track of selling. Maybe it's not a car, maybe it's something smaller. Who knows? Like we just have now a way to facilitate the transaction, have an escrow service, and this service is available to people where like this was never conceivable before. So like, I think that there's different levels to this. Like, I think a lot of these things feel very like, why bother as Americans? Like, I don't really have that many problems buying a car. Like, it's annoying. I do it twice a decade. And like, it sucks for that little bit. But like, these things, if we make them easier, if we make them cheaper, suddenly we can take these same things, we can spread them throughout the world, and like, nobody has to run it. Like, we can do this stuff for free. In the same way, like things like Wikipedia and Facebook have, empowered people in these kinds of places. Like, I think having access to a money system that is theirs, I think that could open a lot of doors for a lot of people. I don't remember what your original question was. So, this I think is a really cool tutorial, because all of that stuff I just said, like, it's a lot to take in, right? But these guys have boiled it down to a simpler idea, which I think helps people learn how this stuff works pretty well. Instead of taking over the financial world, we're going to use this database to store information about a video game. And the video game is one, it uses, they call it as crypto collectibles. There is, so the smart contracts, right? They are code that runs in the Ethereum, in the in the wherever. One flavor of smart contract that people have come up with is one that represents, think of like a collectible. Think of like a baseball card, right? It represents something, think of like Magic the Gathering, Pokemon. You have a card, you collect them, kids like them, people tend to make games out of them. This particular one is instead, it's meant to model Magic the Gathering kind of games where, you know, you have two people and they both have a deck, right? Like, I don't know how these games actually work, but they both have a deck, and then one person plays cards from one deck, and it hurts the other guy's boss, and then you play, and then whoever's boss dies first, that's who wins the game, right? So, in this tutorial, what we're going to do, and if you click here, this is at cryptozombies.io. Like, I'm going to go slow, so please follow along. I think that'd be good. And if somebody next to you needs help, please help them. We're going to go part 1 here, making the zombie factory. Maybe? Oh, I already did it. It is cryptozombies.io. And here they kind of lay out what the goal is. What we're trying to do is, so this database of zombie cards, like when they say zombie, picture a card in a Magic the Gathering kind of game. It is a character that has some sort of attribute, and over here you can kind of play with what the attributes are. They got ones for the head, they got different eyes. If you look, you can see, like, it's hard to see up here, but you can see as you move this, it updates a number there. So, like, a zombie at its core is really just, it's like a record in a database that is, let's see, we got eye color 535, skin color 304, 0, 0. It's just a record in a database that keeps track of the attributes of this particular zombie. So, our factory is going to maintain a database of all the zombies in our army. Our factory is going to have a function for creating new zombies. And one of the things is that each zombie is going to have a random and unique appearance. And that random and unique appearance is driven by these numbers over here. We got close. All right. So then, in later lessons, they go through and add more functionality. Like, you can have zombies. They can have the ability to attack humans or other zombies. But we're going to add basic functionality first. And okay, so here they got a description how zombie DNA works. Okay, so this long number here, let me blow that up if I can. Nope. This long number here. So we're going to generate what they call zombie DNA. And zombie DNA is a simple 16-digit number. Here it is, 16-digit number. And the idea being each two of the numbers, so 83, they're going to do some math. And they break down what the math is down here, but it's not that important. They do some math, and they turn 83 into a number from 1 to 10. And then they use that to pick which like the first two numbers would be the eyes, the head, second two digits are the eyes, etc. So like this 16-digit number, it just represents the attributes of our zombie. So it represents the information that we're going to store, like, so we got 83. That would boil down to this, and then the second two digits would be this one, and the third two digits, and so on. All right, so they go into more of what that means. Okay, here's the actual math they do. So let's say the first two digits are 83. They're going to do modulus 7, add 1, they get 7. Essentially, 83 equals 7, and then that equals what shirt I have. So if you play around with the sliders, you can see how that works. But we already did, so we're going to go next. All right, so this is the first important chapter. The contracts. So, okay, one, Ethereum is the name of the network of computers. Yeah, what's up? It is Solidity. It's Solidity. So Ethereum's the network of computers. Solidity is the programming language that we're going to use to write a smart contract. So like Solidity is their version of C#. And Ethereum, I guess if I were continuing the analogy, would be like a self-hosted Azure that's running itself. All right, and okay, so a contract, it works a lot like a class in a conventional object-oriented language. It is like the first place that we need all the variables that you make, all the functions that we make, they're going to be part of a contract. And it kind of works like I don't know if a singleton is the right word, but when we make a contract and we deploy it to the network, there's only one of it. So like when I'll get to that in a little bit. That'll make more sense here in a second, I hope. So so over here, hello world, we're not actually going to do hello world, we're going to do something slightly different, but the same thing. But if we were making an empty contract called hello world, this is what it would look like. It would have the keyword contract, the name of our contract, curly braces, looks just like JavaScript or Java or C#. Okay, so one of the first things that we have to do is in Solidity, okay, so remember this code is going to run forever, right? We don't know what the Solidity code is, the Solidity, virtual machine is going to look like forever. So what they make you do is they make you choose which version of Solidity you're targeting your smart contract for. Like, I want it when this code runs, I want it to run, and here we're doing 0.4.25. I want it to run with this particular rule set, and that's the rules it's going to be. And even if there's new versions of Solidity, we're going to ignore them. I want this rule set. Because over time, the rule set could change, and if like how the compiler works changed over time, that could change my code, and I don't want that. So I want to lock in saying use this version. So we do this with this pragma Solidity, and then we say the version number. So you need this little caret 0.4.25. And then we need a semicolon. And they have that as the latest version, but it's actually, there's a newer one now. Not that it matters. And then, so they got more hello world. And then what we're going to do is we're going to make a contract called Zombie Factory. And we're going to set our Solidity version to 0.4.25. And then we're going to create our contract. So we're going to say contract, Zombie Factory, and then we need semicolon, or not semicolon, curly braces. And hopefully that should be good. If it worked, you should get a dancing zombie guy. If it didn't work, say something, we can help. Yeah.
If you want to add another attribute, you're locked into that, you have to create a new one. That one holds forever.
Yeah, so, yeah, like, one of the challenges to writing these smart contracts is that the requirements do change. So if you want to add new attributes in a new version, you have to deploy a new version of this contract that is completely detached from the other one. And then there are, like, strategies. So it's like any kind of code, right? Like they've come up with strategies for making libraries of like common code, and then you pull in old stuff through that. Like there's ways to make it happen, but yeah, you have to code it. It can be challenging because like you have to. There's no do-over, right? Like it makes testing. It makes things like automated testing and writing like unit tests, like hundreds of unit tests, like very, very important to like how these things work because there's no second chances. Like you put it out there, it's going to have to work. You better have tested it because it's going to work exactly the way you mess it up. In ways, yeah. But the nice thing is like over time, it's like any ecosystem, right? Like, over time, people start finding the common things that you need to do, right? And, like, there exist contracts that work like a common library where, like, yeah, you do have to plan up front, but you don't necessarily have to implement every little thing yourself. Like, that's definitely, for sure, yeah. Yeah, like, that's probably more advanced than I'm going to get into right this second, but like there are strategies for mitigating that, and it involves writing code that can be complex sometimes. Yeah. All right, so the next thing we're going to do is we got a contract, and now we're going to learn about how Solidity deals with variables. There are a couple different kinds of variables in Solidity. And the first one we're going to talk about is, it's different than any other language's first, like, variable. So, in this example here, where we make a contract example, and then we're making one variable. We're doing uint, so it's an unsigned integer, so it can go up to like, I don't know, 4 billion or whatever. And then we're giving it a name, and then we say equal 100. In most languages, C#, what that would do would be you'd have in your memory, in your computer's memory, they would be pointing to 100, and then that variable would be 100 until your computer turned off, and then that would disappear, right? This does not work that way. In Solidity, when you do this, you are writing a permanent ledger. You are writing a permanent marker in that global ledger that costs money to put that information there. So this is called a state variable. And state variables are permanently stored in contract storage. It's you think of them like writing to a database, and writing to a database where you have to pay a little bit of money to write to it. So like, you have to be careful with how you allocate resources. Like, this is, I hope all of the guys who made SQL in the 80s are still alive, because we need them to write libraries on top of this stuff, because it is very difficult. There is a very small amount of memory that you have to work with, and a very small amount of disk space that you have to work with, and there are like limitations. And so this is a very expensive operation that you have to make sure that you want to do it. All right, so in our example, we're storing 100 in our contract storage. All right, so uint, this just means that it's a very big number. It can't be negative. That's all you need to know for that. All right, and what we're going to do is in our contract, remember we have our 16-digit number that represents our zombie DNA. We're going to store that number in our contract, and that's going to represent our zombie. So we're going to declare a variable. Well, actually, we're going to say that our DNA is 16 digits long. My bad. Actually, that's what we're going to do. So we're going to make a uint. It's going to be called DNA digits, and it keeps track of how many digits that our DNA is. So uint and DNA digits equals 16. And then you need a semicolon. How you guys doing over there? Good? Good? Okay. If you need help, please say something. If you fall behind, it won't be as fun. I'd rather wait. All right, so math and Solidity. It works like math in any other language. You have addition, plus symbol, subtraction, minus. We got our asterisks for multiplication, division is a slash. We got a modulus. Works exactly the way you expect if you are familiar with any other language that does math. And then they mentioned that there is one other operator that it does support, in that they got this exponential. So 5 to the second power, which would be 5 times 25, not 5 times 25. 5 times 5, 25. So what we're going to do, oh man, okay. So they want us to, okay, so to make sure our zombie's DNA is only 16 characters, let's make another integer equal to 10 to the 16th power? Why? That, yeah. So they're doing some math operation here. Yeah. I think so. Yeah, it's definitely related. So we need to. So they're trying to shorten an integer to 16 digits. So we must have a longer number somewhere. I see. That makes sense. No, yeah, no, that makes sense. Yeah, so it's gonna be longer. Yeah. All right. So we're going to create a uint. We want to, under where it says start here, uint DNA modulus equals 10, and then we do asterisk DNA digits, right? And that's what it's asking us to do. Set it equal to 10 to the power of DNA digits. Everybody get that? Okay. So the next thing we talk about is structs. And these are, all right, so one variable what allowed us to store one number in storage memory. Sometimes we need to store information that's related to each other. Think of like a table row. When we have a row and a table, represents customer's account. So we might make a struct for the person that has their age and their name. So in a practical sense, struct it kind of represents a row in a database that is all associated together. Like you store the whole thing in the database together so that the age and the name, you can reference them at the same time. Structs allow us to create more complicated data types that have more than one property. And let's see, they're just making a note here that also they happen to they defined a string, which is just arbitrary text. But it's also very expensive. Like a string in Solidity world, like you want to make sure that this is a string you need to save, because it is storing arbitrary length information right now can be very, very expensive. So you typically want to be very conservative about how much information you store. So use a string when you absolutely have to, but that's the only time. All right. So in our app, we're going to create some zombies. And a zombie is going to have multiple properties, just like the person. So what we're going to do is we're going to create a struct. We're going to name it zombie. And our zombie is going to have two properties, a name, which is going to be a string, and the DNA, which is just going to be a number. So we're going to do struct zombie. And then curly braces there. And then we just do string, name, and uint DNA. So we haven't actually made a zombie yet. All we've done is defined, here's what a zombie looks like. It has a name, it has DNA, it just has these two properties. And then up here we've started writing the rules for how you build a zombie. So if you hit check answer, should be good. And if you haven't figured it out, if you look down here, so if you get it wrong, they actually will show you the answer. Oh, I have it kind of hidden. But it's down here, if you can't get it. Questions? Like, I got structs, got variables. Okay. They also have arrays. Like anytime we want a collection of things, the first storage type that we want to use is an array. And in Solidity, there are two different kinds of arrays, and they're distinct in a way. We have an array that has a fixed length, and what you do there is you say what type it is. So we're going to make an array. All of the items in the array are going to be unsigned integers, and we want 2 of them, and then we're going to give it a name, and then that array can hold 2 items for the rest of eternity. Like, that's the only information you can ever put in them, are those 2 pieces of information, those 2 numbers. And here they have another example, same thing, string array. We got the type, it's a string, we want 5 of them, naming it string array. We can hold 5 of them. This one is way more useful most of the time, especially in this context. It's a dynamic array, and this can hold as many as you need. Like, there are practical limits maybe, but there are no limits to the amount of, in this case, it would be unsigned integers that you could put into this array. So remember, when we make a variable like this, we're making a storage variable. So somewhere we are actually writing to a file all of the information that we put into this array. So when we say this is arbitrary length, this is like dynamic length, we're kind of defining a table. Like, if you were to make an analogy to an existing system that has a database, this array is a table that it has 1 column that holds numbers. And, yeah.
So, once the variables or the structs or the arrays get assigned, right, you don't go back and change them, do you?
Correct, yeah. Like, well, so you can add stuff to them, to the end of them.
Wouldn't that make it a new contract?
So your contract,
Then it's a new contract. It's not the same contract. I've got a contract that I want to live forever.
yeah,
Right?
yeah.
I mean,
So what you can do, you deploy the one contract that has this array in it, right? And
so I deploy the instance of that contract.
yes. So yeah.
Yeah.
Yes. You deploy the instance of that contract. It creates this array.
Right. Now it's out on Ethereum's blockchain. It's in their ledger, right?
Yes. And you can make a public function, essentially, on your contract that would allow you to put more information in this. So you could have a function like add number that takes in a number from outside and then writes it to this array in the same way that you would write to a database table. So like this would make this available to our zombie factory. But then like we can add functions later that allow us to manipulate it in ways. And those functions can be callable from outside. So like users can pass us stuff, can pass us information, and then we can store it in an array.
So where does all this stuff get stored? So you write the contract, and then suppose, so you write it, and then where does it get stored?
So where it gets stored is in the Ethereum network. And where that is on, so the Ethereum network, it's a distributed database. So everyone connected to the network has a copy of this database. And what you're doing is essentially, when you add to it, you're sending out a message to the network saying, hey, I want to pay to put this information in this slot. So I'm going to write it to my local database, and then you all write it to your local database too. And then this is going to be there forever. And then we all agree on that. So, like, when you read the information, it becomes very free and very cheap because all you're really doing is, like, querying your own database. But writing becomes a very expensive operation. in various ways.
This one you're talking about is the public Ethereum network. So do you have private ones that you can set up like these contracts?
Yeah, I mean, I'm not familiar with them, but yes, there are definitely companies that are working on implementations of the Ethereum virtual machine that like private companies are setting up amongst themselves. So like, yeah, like there are a bunch of different use cases where like maybe the permanency is less important to the company as like I need it to work faster. So like you may make a private version that like removes some restrictions, but then you can't trust it either. So like there are trade-offs. But yes, there are definitely companies working on that. But what we're writing to would be the public chain, which is accessible by everybody. So here, this is where we start to become, like, this is where things start to get pretty useful. Where we make an array, we can make an array of structs. Which means, like in this example, now if we made person records, remember every person has an age and a name. We made person records, we could stuff as many of these as we wanted, as for as many people we have, into this array, which when they get saved and shared on the blockchain. So this starts to function a lot like a database table that has person records in it. All right, so there are some, like I was mentioning, there are some rules that you can use. So like, one of the things you can do is you can have Solidity just like make this array available so that anybody could read from it. And what you do is there's this keyword you put on it and you put it in the middle for some reason. You put this in the middle here. We say public, and then I don't have this set up so it'd be hard to see, but like if you were connected through, this is fake money, just so you know. If you were connected to a real blockchain, there would be places down here in your wallet where like you could get this information. The one, where did it go? I'm just trying to give you a reference where you might access this stuff. So like this information, this person information, there are tools that would allow you to read it, essentially, and it's your wallet, right? So like anybody would be able to, what am I trying to say? That's not forget what I just said. Just forget it. It's over. Yeah. That's exactly right. Thank you. So in our case, what we're going to do is we're going to create a public array of zombies, and we're going to name it zombies. So we need, what's this? We need the type first, so zombie. So it's an array of zombies. It's going to be dynamic. We want it to be public, and I'm going to name it zombies. What was that? Yeah. It's good. So we check answer. Should be good. So we don't really have anything that can do anything yet. Like, we don't have any way to trigger an action of any kind yet. Like, we're getting there. The place where we can actually start to do things, where we start writing code that we can call, is in a function. And this is what a function in Solidity looks like. It looks a lot like a function in any other language. In here, what we have is we have the keyword function, and then we have the name of our function, and then we have parentheses, and we have comma-separated parameters to the function. And one of the things you'll notice is that each parameter to the function, it gets a type. There's no var or anything like that in Solidity. Everything that we make has a specific type. But it looks pretty similar to most other languages, how they make functions. The function we have here is named eat hamburgers. It takes a string called name, and it takes an unsigned integer named amount. And for now, we leave it empty. Oh, and one of the things they note here is that, and they don't even do it, but there are public functions that are callable by the world at large. Like anybody with a wallet can call your function. And then there are functions that are only callable by your own function. Like it's essentially private to your code. And the convention in Solidity is if it's private, then the name is going to start with an underscore. They don't actually have it here yet, but so we're going to start to see we're going to write some functions that start with underscore, and just know that's like a convention that Solidity developers do for whatever reason. All right, so in our app, we want a way for us to be able to create these zombies. Right, so we want to instantiate a new zombie, new person signing up for the game. We want to make a new zombie. We want to generate some attributes for it, make it look a certain way, give it a name. We're going to have to create a function called createZombie, and it's going to take two parameters. It's going to take the name of the zombie, and then it is going to take the DNA, which remember is a 16-digit integer. And then we're going to leave the body of it empty for now, but we'll come back and add stuff here in a second. So we do function, createZombie, and then we want a string name and an unsigned integer underscore DNA. And you can see, like, one of the other things we did is here, we named this underscore name. That's because in Solidity, this is also a convention in Solidity, any variables that are passed to a function are named underscore. So it's like a way to differentiate visually the parameters that are local versus the ones that have a more global scope. And you should be able to check it. Should be good. That work for everybody? All right, so in this chapter, what we're going to do is we're going to create some structs and we're going to put it in an array. So in the previous example, we had defined a struct named person, we give it an age, give it a name, and then we made an array of persons, people, and we made it public, and that's how that became our database of persons. So in this, what we're actually going to do is instantiate a struct of a person and put it into the array. And here they have the syntax for how they'd create a new person. In our example, it's going to be a zombie. But in what they have a person, and then they name their variable, and then the syntax here, it's like confusing in a way because it's like implied, like you didn't make a constructor for person in any way. What we did is it just reads the parameters in the order that they're declared. So in our person here, we have person 172. So when we make a new person, we pass the first one as age, and then the second one is name. So here they pass 172 and name Satoshi. And then in their code there, they have their array. Remember our people. Our people is this thing. And then they call this function push, which what this does is it writes this record to the database. It puts that record into the array, which is stored permanently in the blockchain. So this push, it works a lot like you'd expect a SQL insert statement to work. It takes information, it writes it to this data store, and it writes it to it permanently. And then they have an example of combining it, which they will technically make us do, but it's very confusing, so we'll kind of break it down a different way. But all right, so is this important? No. Oh, so this is kind of important. If the order in which we call push, that matches exactly the order of the information in the array that we're pushing to. So we push 5, 10, 15 in that order. The information in our array would be 5, 10, 15 in that order. All right, so in here, what we need to do, so we're in our create zombie function. And what we need to do is we need to fill in this so that we create a new zombie, we add it to the zombies array, and one of the things it notes here is that the name and the DNA should come from the parameters that were passed, right? So we're going to, in our function, we get past the DNA, we get past the name. We want to make sure when we instantiate our zombie that that's what we add. So let me zoom out here for a second. Okay. Because this is a little longer. So for some reason it wants us to do in one line of code, but I'm going to do it in two, and then we're gonna like make it one line. So we want to create a new zombie. So we're going to say zombie, we'll call it Z, it doesn't matter, equals zombie, and then what was the name? What was the order we have? We have name and then DNA. So we're going to pass underscore name underscore DNA. And then we need a semicolon. So we instantiate our zombie with the name and the DNA, and we assign it to this, which one thing to note is we're inside a function, so this doesn't get written to permanent memory. This isn't a storage variable. This does run in memory the way you'd expect. And in later versions of Solidity, we would actually have to write the word memory here, but we don't have to right now. So this is in memory, and then we have a call to, remember our zombies array up here? We're going to say zombies push, and then we're going to push the one we just made. So we instantiate the zombie in memory, and then we push it permanently to the database. However, this tutorial doesn't like that. So what you're going to have to do is they want you to, see the part I have highlighted here? Cut this, pass it directly, and never have this in-between zombie. So this was the zombie we created, and we're pushing it to the array. I just want you to see this is actually two separate steps that they're combining in the tutorial. Yeah.
So you said the local variables not get written to your Ethereum network, but this operation would affect that because zombies is your state.
Yes. Yeah. Push is the thing that makes it permanent. Like here, when we created this array, we didn't put anything in it. So when we instantiated it, it was like empty. And then here is the first time we actually start putting stuff in it. All right, hit check answer, should be good. All right, so in Solidity, one of the things is functions. By default, whenever you make one, it's public, and that means anyone can call it. And it also means anyone else's library can call it. So other people who write contracts, their contract can invoke your contract which is one of the really neat things that, like, I think is one of those things that makes this, like, so special, is like everybody's writing these contracts and they're putting them out there, and they can interact with each other. So, like, for instance, there's a game company another game company makes another collectible like this. They made a game, it's called Gods Unchained, and then they just made a deal with another game called CryptoKitties, where, like, they're issuing, like, special versions of their card that somehow feature your CryptoKitty. So it's like two game companies that are completely unaffiliated with each other in every possible way. They just happen to notice both of their code is, like, in this place where their contracts can call each other. So, like, why not? So, like, I think it's going to lead to a bunch of different collaborations for things, like, people would never expect. So it's like, sometimes I, like, think of use cases for crypto things, but, like, I would have never thought of cards calling other cards to play a game that nobody ever made.
Don't you need some kind of a reference, though? Like, for example, I'm thinking, like, in the C# world, you need to reference the library, or you need to reference the project of the function where it's at.
Yeah.
So don't you need some kind of a reference here as well?
You do. So the contract, essentially, that code gets deployed to the public blockchain, and then it's visible. So the code itself is the reference.
Okay, but then if you have one function that can call another, or two functions that can call each other, aren't you going to end up with a circular dependency issue?
You are, and there are rules for contracts calling each other. I don't know them off the top of my head, but that's definitely a problem. And then they have other solutions to that too. Like, for instance, to execute the code, it costs something called gas, which is the Ethereum token, right? And there are limits to how much gas you're allowed to spend. Because, yeah, like, people thought, like, yeah, immediately, they're like, oh, I'm going to call this one, make this one, call this one permanently forever, locked up the network. Good luck, nerds. Like, yeah, I mean, they're definitely exploitable things, and, like, they're coming up with rules to try to make it non-exploitable. All right, so one of the things is, by default, it makes them public. So unless you mean it to be public, it is a pretty good idea to mark it by private, unless you actually want people to access it. And they have here an example of a private function that is kind of pointless, but it essentially acts as a wrapper around push that only this contract could call. Limited use sometimes, but all right. So our contract, the create zombie function, is public by default, which means anybody could call it, and we don't want that. So what we want to do is make it private. And then it says, don't forget the naming convention. So we need to make sure we make it private. And then the naming convention is that private functions are named _. So we do that. That was a quick one. It would be for what? I didn't hear the word you said. Bidding. Bidding.
I bid 100 on that. Someone else bids 50.
Oh, I mean, if you were making
Creating an open contract and saying, okay, here's the parameters, join in.
Yeah, I mean, so like people, okay, along those lines, for instance, there's a contract that's popular. It's like, okay, so it's a smart contract that collects money, right? And people send money. like pennies. And the contract is set to pay out to whoever the last person to send it money was, if nobody else sends it money within like a minute. So like, there's like this thing where people are just throwing pennies into this wishing well, hoping that no one else calls it in the next minute. And like the payouts for these things are getting up to the millions of dollars. There was one, it paid out like $3 million. $3 million? People are crazy.
3 dozen pennies, huh?
Well, it was more than that, yeah.
Wow, well, right?
Yep.
Wow.
But like, that's an interesting concept too. Like, there's this game with a huge payout that's currently being run by nobody. Like, it's like the lottery, but I don't know. No, I don't know. There's no, I don't know. It's just like, people are coming up with cool stuff. Alright, so more on functions here. So sometimes you make a function and it's like, I want to ask a question and then get back an answer, right? So the way you do that in Solidity, like most other languages, is with a return value. And in Solidity, you are explicit about what you want to return. So you use the returns keyword, and it comes at the end, basically, of the function. You say function, you give it a name, you say it's public, and then we're going to say returns, and then you say what it returns. This particular function returns a string variable. So that means whoever calls it knows that what they get back is going to be a string. And it also enforces that your contract will not compile unless you actually return a string. So it forces you as a developer to actually follow rules, which some people don't like. All right, here's a note. So we have a couple different kinds of functions in Solidity. And it comes down to, like, we have this database, right? And you have the database and it's running on your computer, essentially. And it's very expensive to write to, but it's very cheap to read from. So if you have a function in your contract that you expect to be read constantly, maybe, and let me see. The actual rule is that it can't manipulate the state. Like those storage variables, the arrays, like it can't be something that actually creates storage and like changes variables or writes something to the database. It has to be a function that just reads stuff and returns it. And by marking it view, you essentially make it free. Like you don't have to pay gas to execute it. And nobody has to pay gas to execute it. So view means that it reads data. Pure is like another level above that where it doesn't even read data. All it does is maybe it takes in two values, it multiplies them together, and it returns the result. So like, it may do calculations, it may do logic, but it doesn't read any data from the database, and it doesn't write anything when it's done. All it does is it executes code. They call this pure.
So then the underscore for the variable names is only if it's reading from the database? Because earlier you said in function declaration you were required to have an underscore in the naming convention.
Yeah, so like, okay, so here it's on the function name. Here, yeah, you're right. I would expect these to be underscore too. But that's a convention. It's not enforced by the compiler. It's just like as the applications get more complex, people have come up with like their own rules. Like, hey, let's start naming these. They're like underscores, so we know what they are. But they must not have done it for the tutorial. Do you have a question?
Is it only public functions that cost gas, or do private functions cost gas as well?
So public functions are, a private function could cost gas, but it would be executed by a public function. I'm sorry, the private function that costs gas, like it's not going to be costing gas directly in the sense like you'll have a public function that calls the private function, and since the public function calls it, like when you call the public function, you need to pay the gas then. So it's like pass-through gas.
Rephrase.
So this database, right, that is immutable, like it has the math that makes it so you can't change. Like there are people running that network, and they're not a charity, and they want to make money, and they're trying to essentially, this is how they are making money to secure the network. So you're in paying the gas, you're like contributing to keeping the network up and running. You're paying for hosting, yeah. That's exactly right. And like it's a pretty good deal right now because, yeah, yeah. Also, the price of Ethereum is super cheap right now, so gas is super cheap. It's like, I don't know, 100 and something. It was way higher. No, the gas fees depend on which function you're calling. So like a function that is very simple and only runs 2 lines of code that are very simple might cost a penny. But if you're running a function that's very, very complex, like deploying a game, like that may cost a little more money. So it depends on the complexity of the contract that you're executing. But the analogy is right in the sense where the gas fees are essentially you buying the processing power or the storage power of the network.
So you can't like set a price for the smart contract for how much gas it costs. It's just how much the computer.
Yes. It's how much it takes, yeah. It's a distributed network, and it's distributed. So every node in the network, what happens is when somebody executes your smart contract, right? Everybody running the network has a copy of the smart contract. Like you deployed it to the network, you paid gas to get it deployed to the network, and now everybody on the network has a copy of it. And then somebody comes along.
Are you also on the network?
You can be. You might not be.
But you don't have to.
You don't have to be. You're accessing a node via some mechanism. Like, for instance, you may have set up a node that you're logging in to do it, or maybe you're renting a node, or there are a bunch of different ways you can do it. There are a bunch of different wallets, too. But, so, the contract gets deployed, and everybody has a copy of it, right? And then somebody comes along, and they want to execute your function. What they do is they send a signal to the network saying, hey, I want to call this function with these parameters. And then the network goes, okay, it's going to cost this amount of gas for you to do that. And then you send that gas fee along with it. And then what happens is everybody on the network runs your code. Your code runs on everybody's computer in the network. And then once a certain percentage of the network agrees that this code executed and it made these changes to the state and it returned this thing, like once you get consensus about how this code changed the state, then that new state gets written to the blockchain. So it's just like, okay. There is no central place. Yeah. Yeah, what's up?
How does that happen, actually? I mean, if I've got 1,000 computers that are, or 1,000 developers, let's say,
Yeah.
and they run this test, and there's no central point of control, how is it that they know when to stop broadcasting the data chain out?
So, I don't know. The answer is I don't know exactly. The mechanism is complex, and it has to do with they have figured there is a system of distributed consensus, and I don't know exactly how it works, but the idea is that we all run as part of the node. If we're running a node, we run the code, right? And then there's math. So like, you hash things, and then I don't know honestly. Like there's a lot of moving parts. I'm not an expert at the consensus part of it. I've been building apps on top of it. Like it's I don't know. I hope that helped. Yeah.
Do that 256-bit or whatever. I mean, that's why when it completes, you get a Bitcoin or whatever if you're mining.
Right.
Because you took a lot of CPU and everything to create. So that's what makes the consensus.
Yeah, you're paying. Yeah, you're paying for everyone to run your code and agree what the outcome was. Like that's like the idea. Like the general idea. How they come to that consensus, I don't know exactly. But like the idea is I pay the network, they run my code, they agree through whatever mechanism they have. I assume it's some sort of network connection where they compare results. Like I don't know exactly. But like yeah, like they come up with consensus, and then once they agree with what that state looks like, then the data gets written and it gets fed through a hash function where now like those transactions became a permanent part of the blockchain, just like the transactions that moved money from account A to account B. So like it's an extension of what Bitcoin did with ledgers, but just applied to different data.
So what kind of scale of time are we talking about for that consensus to occur? I mean, is this milliseconds or is this minutes, hours?
So it depends. One, it depends on how much you're willing to pay.
Okay.
So if you pay more, so essentially whenever you put a transaction out onto the network, where it's going is like this in-between world where it's like a pool of here's all the transactions that people want to run, right? And then if you're running a mining computer, you've got this little mechanism that sorts all the transactions by who's going to pay the most. And then I'm going to go down that list and I'm going to do the transactions that pay me the most as a miner. Right? And then once I've done that, I compare my results to everybody else's. And like, if we all agree that these are the best transactions to run, which we probably will if they're the most expensive, those are the ones that get included into the next block, which is like every like 10, 15 seconds. So every 10 to 15 seconds, the computers are racing to come to a consensus about what happened. And then after that 15 seconds, it gets locked in like permanently. So like, but like also, if you're fine being at the bottom of the list and you're like, I don't really care. I'm paying my grandma. Like, this transaction could go through whenever. Like, maybe I don't care if it takes a day and a half. I may pay way less money. I may pay a quarter of a penny, and maybe it takes a day and a half, but it goes through eventually. So, like, it's up to you how important the transaction is to you.
So, and you may not know the answer to this, but is there something built into that algorithm to make sure that a transaction doesn't get starved? So, like, if I only want to pay a quarter of a penny,
Yeah.
is there at least a guarantee that it's going to finish within some amount of time?
No. So so there's a risk there. There's a timeout period. Like, if it doesn't get picked up by the mining group, like within a day or two, it just gets dumped and it gets forgotten about forever. And it's like it never happened.
Do you get notified?
No.
That would be
Yeah.
a major problem.
Yeah. Okay. All right, so yeah.
So then, are there companies that are tied into the Ethereum network whose their purpose is then to kind of be the brokers of these things, right? They're the ones that you're going to subscribe to or whatever to use this. Is that a true statement or not?
So there are a lot of different companies in the ecosystem. And some of them are part of running the network in the sense where they have the mining computers and all that. And then there's like people who are building infrastructure on top of it in the sense where there are companies that are building, like, say you want to run a Facebook, right? With what we're doing, Facebook would be very expensive to run. But, like, there are companies interested in making things like Facebook, and they want an environment where, like, some of the rules get laid down a little bit, right? And there are companies building what we call second-layer networks that are built to, like, provide a whole bunch of processing power to these smart contracts in a way that's, like, cheaper. So, like, there are companies that are building in that way. There are companies that are building things called decentralized exchanges, which, like, these tokens, like Ethereum, or like even our zombie, right? Like, say I play this zombie game, and the zombie game gets popular, like Fortnite, and I want to sell my zombie card to somebody else. There are companies that their sole purpose is to facilitate the trade of these tokens between each other. So, like, maybe someday, like, my house and my car and the title and the bank and all these things are on the network, and, like, there's a company set up to facilitate those transactions in similar ways to the current system. Yeah. All right, what we're going to do, we're making a helper. So here we're actually going to make the random DNA number. We're going to create a private function. We're going to call it generate random DNA, and it's going to take a parameter, and it's going to return the 16-digit number that we've been trying to build. All right, so we're going to create function generate random DNA. And it's going to take a string underscore str and returns uint. And then it says this function will view some of our contract's variables but not modify them. So we're going to mark it as view, which did not change the color. And we're going to leave the function body empty. Didn't like that. No, that is not. Thank you. All right, private view. There we go. Oh man. So here, all right, so okay, so remember we got the network, right? And it's like 15,000 computers spread across the world, whatever. My code comes in, and we want to generate a random number. Generating random numbers is very, very difficult in this mode, because we've got 15,000 computers that are all going to run my function, and I want them to come up with a random number and all agree on what they came up with. Right. So generating random numbers is very difficult. Although, like, over time, they've made some progress. But, like, not here. The progress is not made at our tutorial. So, what they have us do is they've got this big, long thing where they break down what we're trying to do. But, essentially, we're going to make a pseudo-random number that's random looking. And then we're going to use that to, like, come up with a random number. So it's not random, but what it does is, what's that? Oh, this function kekak256, what it does is it takes in a string like this, quote AAAB, and essentially returns a big long hash like this. So what we're going to do is call this twice, get two big hashes like this, and remember that thing we did earlier with the modulus and the 16 digits? Like, we're going to use that to shrink that down and do a 16-digit number that's like pseudo-random. We are jumping through all kinds of hoops to get a 16-digit number that is vaguely random looking. And then I'm going to actually do that before we go on. So we're going to fill in the body of our generate random DNA function. All right, so this, oh man, okay. So first line of the code should take, so we're going to do kekak256. And then we need to pass it this ABI.encode packed that takes the string from above. So the first thing we do is we take this string we're getting handed and we pass it to these two functions. And like, it's a big long thing, but all it really does is it takes that string, pops out a hash. And then we are going to store it in a variable called rand, and then we pass it to a function called uint. This is something. So we pass our string to our functions here that turns it into this big long thing, and then we cast that to a number. So what we end up with is a number.
Turn a string into a hex value. Turn the hex value into an int, and then store it.
Yes. So I guess that's going to be a big long thing. So we want our DNA to be a 16-digit long number. Remember these two things we made earlier? So what we need to do is return rand modulus DNA modulus. So we build this big long number, and then we're going to do modulus from, remember this thing up here, this 10 to the 16th power, which apparently gives us a 16-digit number. Semicolon? No C. There we go. So that was that. And we only have a couple minutes left, so I'm just going to type this out so we can see it. So what we want to do is create a public function, create random zombie that takes a name, and it needs to be public. And then what it's going to do is it's going to call this function we made up here. Remember, we made this private function? So here we got a public function. It's going to call our private function. And it's going to get a uint. We'll call it rand DNA. And we'll say generate random DNA. And we pass it the name. And then we pass that to, we come up with our random DNA. And remember, our create zombie function, all it takes is it takes a name, and then it takes a number that represents the DNA. So this really is just a big long thing to come up with a random number and then pass it to this function. So we'll say create zombie, takes in a name, takes in rand DNA, and then events, don't need right now. If you get to the end here, what you can do is you type in your name, and you can see it generates a zombie for you, and breaks down, I got that head, that eyes, that shirt, etc. Yeah. I think that's true, yeah. 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 So it's random. Yeah, it's essentially hashing your name and then adding that to, or doing the modulus on it, or whatever. Any other questions? It doesn't.
They pay to create the art.
Yeah.
You don't receive any revenue, you don't pay anything, it's just that.
Correct. Although, like if you were making a business, you could make part of the smart contract to be to collect money from them and send it somewhere. Like, for instance, there's a bunch of companies working on insurance projects where they'll collect money for, like, there's one that's pretty popular right now for flight insurance. Like, they collect, you're essentially gambling on whether your flight is going to make it. And if you're wrong, you lose, but you get on your flight. But if you're right, you win money. I mean, yeah, you don't want to be too right. Yeah. Yeah. This is essentially like, I have this flight, it's super important I make it there. If I don't make it, I at least want like $8,000.
How are they guaranteeing that everything is secure? Is it backed up? Is it, I mean, even banks are being hacked.
So the entire network is secured with these cryptographic public and private key encryption is the root of the technology that they're using. And then they use that to create distributed consensus. So like the security of the network is built in to how the network functions. Like you can't make a transaction in the network without having the legitimate private key of the account.
And nobody can hack it.
No.
You have to have a really high functioning computer to process.
You know when you go to a secure site and like you see the SSL and it's the connection secure, we have secure HTTP. It's the same exact encryption that secures HTTP is the stuff that's securing these transactions. So like if you believe in the internet, we've already bought into the security, so
I mean, that being said, though, security and smart contracts is a huge thing because, like we were saying, like once you write it, you deploy the contract, like it's done, it's out there. So if you've written bugs into it that allow people to do things you didn't intend for them to do, like it's a problem that is difficult to fix because you can't just remove the code or just patch it up and release a new version and it's like the old one went away. So there's definitely security concerns with smart contracts, but the things that there's companies like Zeppelin Security that like their whole thing is securing smart contracts. They put out like templates of like secure functions in certain contracts that help people develop more secure programs. So you know the security in the network is built in, but of course you know as programmers we can always introduce problems if we're not careful.
yeah.
So can you disable a contract at some point?
Nope. You could write the contract in a way where it disables itself at some point. So it's still code, but no, you can't like undeploy it.
So if you don't want anybody else to, like, grab another instance of it, there's no way to do that.
Are you saying that it would shut itself down basically, so you can, when the contract starts, it would check to see the date and time, and if it's past the year 2020, then it will no longer function,
You could write code that did that, yeah.
but it will permanently be out there.
Yeah.
We definitely need to continue this conversation over a beer afterwards.
Yeah.
All right. Thank you very much, Pat.
Thank you. Thank you, everyone.